Every year, military jets accelerate past 761 miles per hour, but most pilots never explain why. Pushing an aircraft past the sound barrier isn't just about engine power, it's about physics fighting back. When a jet approaches Mach 1, the airframe experiences forces it was never designed to sustain. The metal heats up to extreme temperatures. The wings flex beyond their intended limits. Fuel consumption skyrockets, leaving pilots with dangerously narrow windows to operate. Historically, pilots who didn't respect these constraints paid the ultimate price. Multiple crashes stem from structural failures triggered by sustained supersonic flight, pilots chasing speed records without understanding their aircraft's actual breaking point. The faster you go, the less margin for error remains. On August 22, 1989, Captain John Clark was piloting an F-16 Fighting Falcon over the desert near Edwards Air Force Base when something went catastrophically wrong. At 35,000 feet, during a high-speed climb pushing Mach 1.8, the aircraft's airframe simply came apart. The jet disintegrated in mid-air, and Clark died instantly. The investigation that followed revealed a brutal truth: the F-16's aluminum skin had been weakened by metal fatigue. Every supersonic run creates microscopic cracks in the fuselage. These cracks don't heal. They compound. Over months of repeated high-speed operations, Clark's aircraft had accumulated enough structural damage that the combined stress of that final climb exceeded what the metal could withstand. The wings separated first, then the fuselage buckled like a crushed soda can. This wasn't pilot error. This wasn't a design flaw. This was the inevitable consequence of pushing the same machine past its limits over and over again. The F-16 is engineered to handle supersonic flight, but not indefinitely. Metal fatigue is invisible, progressive, and unforgiving. Clark's tragedy became a stark reminder that every aircraft has a finite lifespan under extreme stress, and ignoring that limit kills. When a fighter jet punches through Mach 1, something invisible but catastrophic happens. Shock waves form along the entire airframe, sudden, violent pressure discontinuities that compress air so violently it heats to thousands of degrees. But here's where it gets dangerous: these shock waves don't stay put. As the aircraft accelerates further, they migrate across the wings and fuselage in unpredictable patterns, and each migration dumps or strips lift from different sections of the plane simultaneously. Imagine the left wing suddenly losing lift while the right wing gains it. The aircraft doesn't politely bank, it snaps into an inverted dive. Pilots call this transonic instability, and it's almost impossible to recover from once it starts. The shock waves create a feedback loop: the aircraft pitches, which changes the shock wave position, which worsens the pitch, which intensifies the shock waves. Within seconds, you've got an uncontrollable spin. The F-15 Eagle experienced this exact scenario during speed runs in the 1970s. Pilots pushing past Mach 2.4 encountered violent pitch oscillations they couldn't control with conventional stick inputs. Modern jets have computers and canards to manage this, but the underlying physics remains brutal. Speed creates the very instability that destroys the aircraft trying to achieve it. Here's what modern air combat doctrine doesn't advertise: speed kills, but not always the enemy. Today's fighter tactics rely on turning radius, acceleration, and fuel reserves, not top-end velocity. A jet that bleeds energy at Mach 2 becomes a sitting duck. Yet pilots still chase velocity records, and that disconnect has proven fatal. In 2007, a U.S. Navy pilot pushed an F/A-18 Super Hornet into a high-speed dive to test performance limits. Structural failure occurred at sustained supersonic speeds. The airframe couldn't handle the thermal stress and shock wave oscillations. What kills modern fighters isn't the speed itself, it's the obsession with it. Combat scenarios demand sustained turns, rapid deceleration, and precision control. An aircraft traveling at Mach 2.5 with empty fuel tanks is worthless. Pilots who understand this live longer. Those who don't become cautionary tales. The fastest jet ever built means nothing if the pilot blacks out from G-forces or runs out of fuel over hostile territory. Engineering exists to constrain performance for survival. Breaking those constraints doesn't prove capability, it proves arrogance. So here's what we've learned: every fighter jet has a hard speed limit. Engineers don't set those numbers arbitrarily, they're based on metal fatigue, shock wave behavior, and structural integrity. When pilots push past those ceilings, they're not proving they're skilled. They're proving they've ignored the physics that keeps them alive. Respect the engineering limits, or become another wreckage statistic scattered across a test range.